What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. Put Saturn in the eyepiece of a small telescope, and it seems almost impossibly composed. The planet is a pale oval. The rings cross the darkness in one clean sweep. Nothing in that tiny view appears hurried. Even the shadows have crisp edges. You can understand why Saturn became the picture people reach for when they want the solar system to look elegant and orderly. But the view is doing something to the truth. A telescope gathers light that has crossed an enormous distance, then compresses a world more than 100,000 kilometers wide into a small image. Motions that would carry an object across a continent become changes of a fraction of a pixel. Cloud layers soften one another through haze. Countless ring particles merge into a bright line because your eye cannot resolve the space between them. The calm is real in the image, but not in the place. Saturn turns quickly enough to distort its own shape. Winds near the equator approach 500 meters per second. Storms can spread around the planet. Every visible strand in the rings is made from material following its own orbit. The picture has not lied. It has averaged, blurred, and reduced until speed becomes symmetry. That is why Saturn looks peaceful from here. Distance hides change by shrinking it below the scale at which you can follow it. Haze hides depth by letting you see only a bright upper boundary. The rings hide their separate particles by packing billions of paths into one luminous form. Move close enough, and the still life resolves into weather, collisions, waves, and falling material. The first correction, then, is not that Saturn is secretly ugly or menacing. It is that beauty and motion were never opposites. The graceful shape is being made by motion. Gravity maintains the rings through orbit. Rotation organizes the atmosphere into bands. Flow draws curves around the poles. What seems finished is continuously being rebuilt. To see the missing motion, you do not need to imagine a hidden catastrophe. You need time, resolution, and more than one kind of measurement. Put images beside one another, and clouds travel. Separate the ring light, and countless orbiting bodies appear. Track a spacecraft by radio, and the planet's gravity tugs its signal in measurable ways. Each method removes a different part of the blur. Together, they turn a portrait into a sequence, and a sequence into evidence. The peaceful appearance survives, but it can no longer be mistaken for a description of what the planet is doing. You have already seen why the quiet disk is a trick of distance. If you would like to help me keep making films with this much care, you can subscribe. Then let us move beneath the haze. The edge of Saturn looks definite in photographs. There is a sharp planet against black space, so it is natural to imagine that the edge marks a surface. On Earth, the visible outline of a mountain belongs to solid rock. On Saturn, the visible outline is mostly a level in an atmosphere where clouds and haze scatter enough sunlight to make an apparent boundary. If you tried to descend there, you would not arrive at a place where sky ends and ground begins. You would enter gas. Above and around you would be hydrogen, with helium and smaller amounts of other material mixed through it. The pressure would rise as more atmosphere accumulated overhead. The gas would become denser, hotter, and eventually behave in ways that have no everyday counterpart. But there would be no single step at which your feet met a conventional floor. Planetary scientists still need a reference level, so they choose a pressure in the atmosphere and call the radius measured there the planet's radius. That is a practical definition, not a hidden crust. It lets different teams compare the shape, winds, and gravity of a world whose visible edge shifts with wavelength, haze, and weather. This distinction also repairs a familiar Saturn fact. You may have heard that Saturn would float in water. The statement begins with a correct calculation. Divide Saturn's total mass by the volume inside its average visible radius, and the resulting mean density is lower than the density of liquid water. As a comparison of two average numbers, that is useful. As a literal experiment, it fails. No ocean large enough to hold Saturn exists. A body with Saturn's gravity would pull strongly on that imaginary water, and the encounter would not resemble a ball bobbing in a bath. Saturn also has no hard shell preserving a neat boundary against the liquid. The comparison tells you that a huge fraction of the planet is made from light elements. It does not tell you how standing on Saturn would feel, because standing is not available there. Imagine continuing downward, past the level used to define the visible planet. At first, the experience would be recognizably atmospheric, although the winds and cold would already be severe. Deeper down, the weight of everything above would compress the hydrogen. There is no universal boundary where an ocean of hydrogen begins beneath a gaseous sky. At the temperatures inside Saturn, the material changes continuously from a gas-like fluid into a denser fluid as pressure rises, long before any imagined traveler reached the deepest layers. Heat and pressure would destroy a spacecraft. The descent is useful only as a way to follow changing matter, not as a route to a buried landscape. The visible globe is enormous. Its equatorial diameter is about 120,500 kilometers, close to 9 Earth diameters. Yet Saturn completes a turn in only a little more than 10 hours. That rapid rotation gives material near the equator a large outward tendency, while gravity pulls inward. The result is an oblate planet, wider around the equator and flattened at the poles. You can see that flattening directly in a good image. Scientists can measure it more precisely from the planet's limb, from radio tracking of spacecraft, and from the way Saturn's gravity acts on nearby objects. The shape is one of the first visible clues that the pale disk is not at rest. Even before a single cloud is tracked, the planet's outline records its spin. The bulge also means that the word down is not quite as simple as it sounds. Gravity points towards Saturn's mass, while rotation changes the effective pull felt by material moving with the planet. Pressure surfaces settle into a shape that reflects both influences. This is why scientists describe Saturn with carefully defined radii instead of one perfect spherical radius. The visible oval is not an optical illusion made by the rings. It is the equilibrium form of a rapidly turning fluid planet. There is a complication hidden inside. The phrase completes a turn. On a rocky world, a fixed mark on the surface can serve as a clock hand. Saturn offers no such mark. Clouds move relative to the interior. Its magnetic field, which might provide another clock, is aligned so closely with the rotation axis that the usual radio method becomes difficult. The exact internal rotation has therefore required inference from several kinds of evidence. For now, the important point is simpler. the globe turns rapidly, while the atmosphere also flows across it. Look at Saturn in natural color, and its bands can seem muted beside Jupiter's. Cream, gold, and faint gray replace Jupiter's louder browns and reds. That restraint is partly a property of the upper atmosphere. Ammonia ice clouds and photochemical haze scatter light before it can bring a clear report from deeper levels. Different wavelengths penetrate to different depths, which is why an infrared view can reveal structures that visible light barely suggests. The color is also seasonal. Sunlight drives chemical reactions in the upper atmosphere, and the amount of sunlight changes as Saturn's tilted axis carries each hemisphere through its long seasons. Haze can grow, thin, or change its optical character. A region that shifts from blue-gray to gold has not necessarily changed its wind speed. Color tells a story about particles and illumination, while moving cloud tracers tell a story about flow. Scientists need both, but they do not treat one as a substitute for the other. Pale does not mean inactive. When scientists compare images taken at different times, small cloud features become tracers. A bright spot appears at one longitude, then appears somewhere else. Follow enough tracers, and a pattern of eastward and westward jets emerges. This is direct measurement of visible motion, with an important boundary. The cloud is observed. The wind assigned to it assumes that the cloud is being carried by the surrounding air, and that the chosen rotation reference is appropriate. Near Saturn's equator, cloud-top winds approach 500 meters per second, relative to the rotating reference used for the planet. At that speed, a parcel could cross 1 kilometer in about 2 seconds. Farther from the equator, alternating jets run in different directions and at different speeds. The bands are not painted stripes. They are the visible expression of air moving through a rotating sphere. To obtain those speeds, a team maps the same feature in images separated by a known interval. Longitude changes, time passes, and the displacement becomes a velocity. Repeating the measurement across many features reveals the jet profile. The answer still carries uncertainty. A faint cloud can change shape between images. Two similar spots can be mistaken for one another. The selected rotation period shifts the reported eastward or westward value. Agreement among many tracers and instruments is what turns individual tracks into a dependable pattern. Rotation bends that motion. When air travels north or south across a turning planet, the ground beneath it has different eastward speed at different latitudes. To an observer rotating with the planet, the path appears to curve. This is the Coriolis effect. It does not create the wind's energy, but it helps organize moving air into jets and vortices, instead of allowing every flow to run straight from warm regions to cold ones. What drives Saturn's atmosphere in the first place? Sunlight matters, but Saturn also releases more energy than it receives from the sun. Heat moving outward from the interior can help stir the atmosphere from below. Moist material rising through cloud layers can release energy when it condenses. Rotation then sorts much of that restless convection into long eastward and westward currents. That explanation is a framework, not a complete weather forecast. The visible bands do not reveal every current below them. A cloud at one pressure level can move differently from a cloud at another. Chemistry changes which tracers can be seen. Haze can conceal the bases of storms. A single photograph, therefore, shows where sunlight last scattered toward the camera, not a cross-section through the circulation. Cassini gave scientists another way to ask how deep the winds reach. During its close passages, radio antennas on Earth measured tiny changes in the spacecraft's motion. Those accelerations mapped subtle irregularities in Saturn's gravity. A perfectly layered, uniformly rotating planet would produce one pattern. Moving mass and departures from simple layering alter that pattern. The measurement begins with a radio tone sent between Earth and the spacecraft. If Cassini accelerates towards Saturn by a slightly different amount than expected, the frequency received on Earth shifts. Repeated across a close orbit, those shifts constrain the gravity field. Scientists express its broad structure through components that describe how mass departs from a simple sphere. Winds matter because moving atmosphere redistributes mass. The signal is indirect, yet it is anchored to a physical effect measured with exceptional precision, the changing motion of the spacecraft itself. Researchers then worked backward through models that connect gravity measurements to possible flows. The resulting inversions suggest that the major jets extend roughly 9,000 kilometers below the cloud tops. That is an extraordinary depth, but it was not photographed. Cassini did not look through 9,000 kilometers of atmosphere and see a vertical wall of wind. The spacecraft measured gravity, and scientists inferred the depth that allowed flow models to reproduce those measurements. The wording matters because an inference can be strong without becoming a direct view. Different assumptions about the planet's density and interior rotation affect the answer. The broad conclusion is that Saturn's familiar bands are not merely a thin decorative skin. They reach far below the clouds by everyday standards. Deeper still, increasing electrical conductivity is expected to resist differential motion and bring the fluid closer to rotation with the interior. This gives the quiet stripes a new scale. A band a camera records as a narrow ribbon may be the top of a circulation extending thousands of kilometers downward. Its energy can come from sunlight, internal heat, condensation, and exchanges with neighboring flows. Its apparent smoothness is the outcome of forces competing over enormous distances, not the absence of force. Most of the time, that competition produces patterns persistent enough to look permanent. Then Saturn reminds us that persistence is not stillness. In December of 2010, Cassini detected the radio signature of lightning from Saturn. Images from the spacecraft and observers on Earth revealed a bright disturbance in the northern hemisphere. It began as a local outbreak, a region where material surged upward and spread into the surrounding atmosphere. It did not remain local for long. This was a case where professional instruments and patient observers on Earth strengthened one another. Saturn could be watched for longer stretches from the ground, while Cassini supplied close images and measurements impossible from Earth. When a bright spot appeared, repeated observations established that it was evolving, not a camera flaw or a passing moon. Radio bursts tied the cloud outbreak to lightning. Infrared maps then revealed heating in the atmosphere above. No single picture carried the whole conclusion. The event became clear because independent methods followed the same place through time. The bright head advanced through a band of flowing air. Behind it, clouds and turbulence stretched into a long tail. Saturn's rotation carried the activity around the planet, while the storm continued to feed and change. Cassini images showed the disturbance wrapping around Saturn, and the mission team estimated the affected area at roughly 4 billion square kilometers. The storm belonged to a planet with room for weather on a planetary scale. The lightning was established independently of the cloud brightness. Cassini's radio instrument detected bursts produced by electrical discharges. A later analysis of the radio data inferred about 5 flashes each second during active intervals. Images provided the changing cloud pattern. Infrared observations tracked temperatures above it. These separate measurements turned a pale mark into a physical story of deep convection, electrical activity, and atmospheric response. Calling it one storm can make it sound more compact than it was. The event included an erupting source region, a moving bright head, a trailing disturbance, vortices, and changes at several atmospheric levels. The visible clouds were part of the evidence, not the entire object. Some of the most revealing consequences appeared as warm regions high above the main cloud activity, showing that the eruption had disturbed the atmosphere vertically as well as horizontally. The bright material was not evidence that the storm had brought a new substance from outside Saturn. Powerful rising motion lifted gases to colder levels where cloud particles could form, making the outbreak stand out against the muted background. The lightning pointed deeper, toward clouds containing water where charge separation can occur. Researchers connect the visible plume to those deeper levels through atmospheric chemistry, thermodynamics, and the radio signal. They did not watch a bolt travel all the way from a water cloud to the top of the atmosphere. Eventually, the head traveled far enough around Saturn to encounter the tail it had left behind. A storm had, in a meaningful sense, caught up with itself. This was not because a single cloud remained intact for an entire circuit. The organized region of active weather propagated through a moving atmosphere until its leading structure met material already transformed by the outbreak. The encounter was followed by the decline of the great visible disturbance, but it should not be turned into a tidy tale in which the head simply killed the tail or the tail poisoned the head. Atmospheric systems contain several coupled processes, and observations do not isolate one dramatic collision as the sole switch. The honest result is more interesting. Scientists watched a global event alter the conditions into which it was moving. Why did such an outbreak occur then? Saturn has produced other immense bright storms, sometimes called great white spots, at intervals measured in decades. The rough spacing invites the idea of a simple seasonal clock, because a Saturnian year lasts almost 3 Earth decades. But the record is sparse, the storms differ, and an interval is not a mechanism. One family of models begins deep in the weather layer. Water vapor rising from warm depths can condense. Condensation releases heat and can drive buoyant air upward, but the surrounding composition may also create a stable barrier that suppresses ordinary convection, while the upper atmosphere cools over years. Energy and moisture can accumulate below that barrier. Eventually, a sufficiently strong plume may break through, releasing energy in an enormous episode. The stable barrier in these models comes from composition as well as temperature. Water is heavier than the hydrogen-rich surroundings. Where water abundance changes with depth, a rising parcel can lose buoyancy, even while condensation releases heat. The atmosphere may therefore resist small outbreaks until cooling creates enough instability for a much larger one. This is a promising physical explanation for long, quiet intervals, but the water abundance and deep temperature structure are not known at every relevant latitude. A mechanism that works in a model must remain inside those uncertainties. This storage and release picture helps explain how a world can look quiet for years and then generate a storm that wraps around it. It also makes testable connections among deep water abundance, cooling rate, plume behavior, and recurrence. Yet it remains a model with incomplete pieces. Scientists do not possess a calendar that predicts the next global storm to a chosen day. The depth at which the outbreak begins and the conditions that trigger it are not directly watched from within. The 2010 event teaches a useful way to read planetary evidence. First comes an observation, such as a radio burst or a moving cloud. Then comes a physical interpretation, such as lightning or rising convection. Then models ask which hidden conditions could produce the observed sequence. Confidence can be high at the first step and more conditional at the third. Saying so does not weaken the science. It shows exactly where the next discovery can enter. It also reveals why a calm photograph can be so persuasive and so incomplete. Most photographs expose for an instant. The storm unfolded through time. Its scale emerged by joining images, radio measurements, infrared maps, and repeated passes. Motion became legible only when many moments were placed beside one another. The visible outbreak faded, but the atmosphere did not simply return to its earlier state. A study published in 2023 used observations from the Carl Jansky Very Large Array to look beneath the clouds at microwave wavelengths. The result was a map of radio brightness across Saturn, and within it were bands that aligned with latitudes where giant storms had occurred. How can a telescope on Earth detect chemistry below clouds it cannot see through? Saturn gives off thermal microwave radiation from its deeper atmosphere. Ammonia vapor absorbs some of that radiation. Where there is more ammonia along the path, less radiation escapes from warm layers below. Where ammonia is depleted, the telescope can receive brighter emission from greater depth. The array measures the brightness at several wavelengths. Researchers then use models of temperature, pressure, and absorption to retrieve an ammonia distribution that could produce those measurements. That distinction matters. The radio brightness is observed. The amount and depth of ammonia are inferred through atmospheric models. The association with old storms is another inference, supported because the anomalous latitude bands correspond to the recorded locations of giant outbreaks. In the retrieved pattern, ammonia was depleted above pressures of roughly 3 to 5 bars and enriched below. The proposed explanation is that storms moved ammonia downward, with precipitation carrying it into deeper, warmer regions where it could evaporate again. The youngest anomaly was associated with the storm in 2010, but other bands corresponded to outbreaks far earlier in the historical record. This suggests that a giant storm can leave a chemical disturbance that outlives its bright clouds by many decades and perhaps much longer. The exact lifetime depends on how quickly Saturn mixes material across latitude and depth, which the observations do not fully determine. The retrieved bands were broader than a single narrow outbreak latitude. That spread is consistent with meridional transport, meaning movement north and south after the event. It adds another inference. Saturn's deep circulation can redistribute the storm's chemical aftermath as years pass, rather than preserving one sharp stain in place. Weather here is not only a visible pattern that fades from the cloud tops, it can rearrange material through a deep atmosphere, leaving a likely chemical aftermath where visible light cannot reach. Once motion is followed through wavelength as well as time, an apparently vanished storm remains detectable in chemistry. That prepares us for the opposite puzzle at the North Pole, where the material changes continually while one visible geometric pattern endures. At Saturn's North Pole, time reveals a different sort of structure. Instead of an outbreak spreading around the globe and fading, there is a pattern that has persisted through decades of observation. From above the pole, a jet traces a shape with 6 broad sides. This is Saturn's hexagon. The name can encourage the wrong mental picture. There is no solid 6-sided frame fitted over the pole. There are no corners made from walls. The hexagon is a wave pattern in a moving atmosphere, wrapped around an eastward jet. Clouds reveal the path, much as leaves can reveal a bend and ripple in a stream without becoming the stream bed. The structure is roughly 30,000 kilometers across. Earth could fit inside its span with room to spare. At its center lies a distinct polar cyclone. The cyclone and the hexagonal jet are neighbors in the same polar circulation, but they are not the same object. One is a rotating vortex around the pole. The other is a 6-lobed wave surrounding it. Viewed in a sequence, clouds move along the jet, while the broad 6-sided form turns much more slowly relative to Saturn. That difference is crucial. If the hexagon were a rigid object, every visible piece would have to remain fixed within it. Instead, cloud features evolve and travel, while the large pattern persists. Scientists can measure both motions. One describes material carried by wind. The other describes the phase of the wave, meaning the location of its crests and bends. Voyager spacecraft recorded the hexagonal pattern during flybys in the early 1980s. When Cassini reached Saturn more than 2 decades later, the North was in winter darkness. Infrared instruments could still trace heat and cloud structure there. As northern spring brought sunlight back to the pole, visible images revealed the feature in extraordinary detail. The combined record establishes persistence over decades. It does not establish that the pattern has been unchanged for centuries. Human observations do not reach that far with comparable detail. The color inside the region has shifted with seasons as haze production changed. Smaller vortices have come and gone. Wind speeds and wave details can vary, even while the 6-sided organization survives. Persistence means the broad pattern endured through the observed interval, not that every cloud held its position. Why 6 sides? The best explanations treat the jet as a fluid flow that can support a planetary wave. On a rotating sphere, air displaced north or south experiences restoring effects connected to the changing influence of rotation with latitude. Waves governed by that setting are often called Rossby waves. Under suitable speeds and surrounding currents, a wave can remain nearly fixed relative to the planet, while air continues moving through the pattern. Think of the difference between a traffic jam and the cars inside it. The crowded region can stay near one location while individual cars enter and leave. Saturn's hexagon is not a traffic jam, and air is not a line of cars. But the distinction is useful. A pattern can persist without being made from the same material at every moment. The corners are locations in a wave, not hinges that force clouds to bounce. Rotating tank experiments and computer models can produce polygonal flow patterns under certain conditions. These demonstrations show that ordinary fluid dynamics is capable of making sharp-looking geometry without a solid template. They do not prove that every laboratory polygon reproduces Saturn. The planet has its own vertical structure, temperature gradients, chemistry, neighboring jets, and depth. A useful analog must still be tested against measured winds and temperatures. Cloud tracking, thermal mapping, and jet models converge on a fluid explanation. The shape is a persistent wave organized by Saturn's polar circulation. Rotating experiments demonstrate that polygonal geometry can emerge from shear without a solid template, although no experiment uniquely reproduces Saturn. Scientists test the wave interpretation by tracking clouds, measuring winds along the jet, mapping temperatures, and watching how the pattern behaves across seasons. A viable explanation must account for its drift rate, its confinement near the pole, its relation to adjacent flows, and its longevity. The observations strongly support a wave organized around a jet. The exact reason this flow selects and maintains such a clean six-fold form remains an active problem. That boundary is easy to lose in a dramatic sentence. It would be wrong to say nobody understands the hexagon. Fluid dynamics explains how a moving atmosphere can support a stationary-looking polygonal wave, and models reproduce important parts of the behavior. It would also be wrong to say the mechanism is completely solved. Competing models differ in the depth of the jet, the role of surrounding currents, and the conditions that preserve the pattern. The central cyclone adds another warning against reading a flat image too quickly. From far away, the polar region can appear as one emblem pressed onto Saturn. Close observations separate a central rotating storm, the encircling jet, smaller vortices, haze layers, and thermal structure at different heights. What first resembled a symbol becomes a system. Now the bands, the great storm, and the hexagon point in the same direction. Visible clouds record motion, but they do not create all of its energy or determine all of its form. The jets descend beyond the layers cameras can follow. The global storm appears to draw on conditions stored below its bright clouds. The polar wave depends on a circulation whose depth is still being constrained. To understand why the atmosphere can move this way, we have to stop treating the cloud tops as Saturn itself. They are the illuminated ceiling of a much deeper world. Beneath them, pressure changes the behavior of hydrogen. Heat escapes from the interior, and rotation couples weather to layers no camera can see directly. The weather has carried us as far as weather alone can go. The next honest step is downward. Downward does not lead from atmosphere to floor. It leads from one state of fluid into another. Near the visible clouds, hydrogen is mostly arranged as molecules, with two hydrogen atoms bound together. That description works because the electrons remain associated with particular molecules. As pressure rises, those molecules are crowded more closely. Collisions become more energetic, and the distinction between gas and liquid becomes less useful. The material grows denser without presenting an ocean surface that a descending observer could cross. Go deeper, and pressure changes the electrical behavior of the hydrogen. Electrons are no longer confined in the same molecular arrangements. They can move through the fluid, allowing it to conduct electricity. This conducting state is called metallic hydrogen, not because it becomes a solid silver metal, but because mobile electrons give it a property associated with metals. It remains a hot, compressed fluid inside Saturn. Conductivity connects the descent to a feature measured far outside the planet. Saturn's internal magnetic field is strong evidence for a dynamo operating in electrically conducting fluid. Its depth, flow geometry, and detailed relationship to metallic hydrogen remain model-dependent. Many arrangements of motion and conductivity can contribute to the field measured by a spacecraft. There is no photograph of this transition. No probe has survived to those depths. The evidence comes from laboratory experiments at extreme pressure, calculations of how hydrogen behaves, measurements of Saturn's gravity and magnetic field, and models required to satisfy all of those constraints together. The broad change from molecular hydrogen to a dense conducting fluid is well-founded. The exact pressure range, temperature, and sharpness of the transition inside Saturn remain model-dependent. That distinction matters because diagrams often draw Saturn as a stack of clean shells. A pale atmosphere sits above a darker molecular layer, which sits above a metallic layer, which surrounds a compact core. Such diagrams help you keep track of changing conditions, but the borders can suggest certainty that the evidence does not contain. Real material can change gradually across depth. Hydrogen and helium can mix differently at different pressures. Heavy elements may be spread through a broad region instead of stored in one hard ball. Helium adds another possible source of motion and heat. Saturn formed mainly from hydrogen and helium, but models suggest that helium does not remain equally soluble in hydrogen under every deep interior condition. In a region where the two become less willing to mix, helium can gather into droplets and settle toward greater depth. Researchers often call this helium rain. The phrase is vivid, yet it should not be mistaken for observed weather. Cassini did not photograph helium drops beneath the clouds. A descending probe has not sampled them. The case is indirect. Saturn gives off more energy than it receives from sunlight. Measurements of the upper atmosphere and models of the planet's evolution also need to account for how helium is distributed. When helium separates and sinks, gravitational energy can become heat. Interior calculations that include this process can help explain Saturn's present warmth and composition. That makes helium separation a physically motivated model, constrained by several observations. It does not make every detail settled. The relevant behavior of hydrogen and helium is difficult to reproduce experimentally across the full range inside a giant planet. Different equations describing the material can move the predicted boundary and alter the rate. The honest conclusion is that helium rain is a leading part of the explanation for Saturn's thermal history, not a shower that an instrument has directly watched. Thermal history is itself an inference across time. Scientists know Saturn's present size, brightness, atmosphere, gravity, and age within the history of the solar system. They calculate how a planet with an assumed starting state would cool and contract, then ask whether the result reaches the Saturn observed today. A model in which hydrogen and helium stay perfectly mixed can cool too quickly. Allowing helium to settle releases energy later and can improve the match. That success supports helium separation as a leading evolutionary process without making it the only possible history. The deeper descent, therefore, replaces spectacle with a more interesting problem. A fluid, made mostly from the lightest elements, becomes dense enough to conduct. Ingredients may separate as conditions change, and heat continues to escape through material no instrument can enter. All of this is happening inside a globe that turns rapidly. To model the interior, scientists need to know how rapidly the deep planet itself rotates. Saturn makes even that basic question unusually difficult. On Earth, you can follow a mountain around once and call that a day. On a gas giant, the visible features are winds. A cloud can travel east or west, while the deeper planet turns beneath it. If you use that cloud as a clock hand, you measure the sum of rotation and weather. Different latitudes give different answers because the atmosphere rotates differentially. A magnetic field can sometimes provide a deeper reference. A field tilted away from a planet's rotation axis sweeps around with the interior. Its changing orientation organizes radio emissions and charged particles into a repeating signal. The repeating period can act as a remote clock, even when there is no solid surface to mark. Saturn almost removes that clock hand. Its magnetic field is aligned with its rotation axis to extraordinary precision. When the field turns, its large-scale orientation changes very little from the viewpoint of surrounding space. The radio signals associated with the magnetosphere do vary, but their periods have drifted with time and have differed between hemispheres. They are influenced by plasma, seasons, and coupling to the upper atmosphere. A variable radio rhythm cannot simply be declared the rotation of the deep interior. The trap is the regularity. A signal can repeat cleanly enough to invite a clock interpretation, while still being controlled by a moving region outside the bulk interior. Saturn's northern and southern radio periods have changed and moved toward one another across the seasons. The deep planet cannot plausibly speed up in one hemisphere while slowing in the other by those amounts. The changing periods, therefore, expose the magnetosphere and upper atmosphere as part of the signal. Periodic does not automatically mean anchored. Atmospheric maps create a related problem. Scientists need a chosen rotation period before they can state how fast a cloud moves east or west. Change the reference period, and every quoted wind shifts. This is why reports can give somewhat different wind speeds without describing different clouds. The observation is the cloud's change in longitude over time. Its wind relative to the interior depends on the adopted interior clock. This is more than an inconvenience for naming the length of a day. Rotation affects Saturn's flattened shape. It changes how pressure balances gravity. It influences how scientists translate measured gravity into a distribution of mass. A slightly different rotation period can lead an interior model toward a different density profile. Before asking what Saturn is made from at each depth, you need the least ambiguous clock available. Researchers have combined several clocks rather than trusting one. They track atmospheric features while allowing for winds. They use the planet's shape and gravity field. They examine magnetic and radio periods while accounting for their variability. Each method contributes a constraint, but each carries an assumption about which part of Saturn is actually turning with the signal. If clouds and radio rhythms will not hold still, what can time the deep planet? The rings offered a different kind of clock. Saturn's interior does not rotate as a perfectly silent, uniform body. Fluid can oscillate. Vast regions can move back and forth in organized patterns, producing tiny time-varying changes in the gravitational field outside the planet. The changes are far too small to see on the globe. ring particles can feel them. Certain waves in the inner C ring cannot be assigned to the usual pull of a known moon. Their locations and pattern speeds instead match the gravitational forcing expected from oscillations inside Saturn. By measuring how those patterns move, researchers can constrain the planet's oscillation frequencies. Those frequencies depend in turn on rotation and interior structure. Analyses using this family of evidence have produced a best estimate for Saturn's bulk rotation of about 10 hours, 33 minutes, and 38 seconds. The precision of that sentence can be misleading if it is heard as a direct stopwatch reading. The measured quantities are patterns in the rings. Connecting those patterns to a single bulk rotation period requires models of Saturn's oscillations, shape, and internal flow. The estimate is powerful because several constraints can be made consistent, but it is still an inference. The rings have become an instrument for a planet they never touch. This technique is often called ring seismology. On Earth, seismology uses waves traveling through the planet. At Saturn, oscillations inside the planet slightly reshape its external gravity. That changing gravity drives waves in nearby ring material. The ring records the influence, and scientists work backward from the record to the hidden source. The word seismology can suggest that a detector is listening to a quake. Nothing so literal happened. Cassini watched starlight pass through the rings during occultations. As the spacecraft, rings, and a distant star moved into alignment, ring material blocked different amounts of light. Repeated brightening and dimming mapped changes in the amount of material along the path. Other observations measured the geometry and motion of the patterns. The data are variations in ring opacity and structure, not a sound recording from Saturn. One occultation gives a narrow cut through a pattern at a particular time. Many cuts at different longitudes and times reveal how the pattern is wrapped around Saturn and how quickly that pattern turns. The local ring particles orbit much faster than the broad wave pattern. Scientists must separate those two motions, just as they separated clouds from atmospheric structure in the hexagon. The measured pattern speed then becomes a fingerprint that can be compared with the frequencies expected from possible internal modes. This comparison is not made by matching a wavy line by eye. A planetary oscillation has a spatial symmetry, meaning a particular number and arrangement of gravitational bulges that travel around Saturn. That symmetry determines which ring pattern it can force and how fast the pattern should rotate. An observed wave must satisfy the location, pattern speed, and symmetry together. Agreement across several waves provides much stronger evidence than a single numerical coincidence. Many ring waves have straightforward external causes. A moon passes a particular orbital rhythm and tugs particles repeatedly. The repeated force builds an organized spiral pattern. Scientists can calculate where such a resonance should occur and compare it with the observed wave. Once those moon-driven patterns are accounted for, a smaller set remains whose pattern speeds point inward, toward oscillations of the planet. That separation is essential. A wave is not evidence of the interior merely because it appears in the C ring. Its speed, direction, number of repeating lobes, and location must fit a planetary mode better than a satellite resonance or another known disturbance. Multiple waves can then be tested against one interior model. A model that explains only one feature while missing the others is not enough. Some planetary oscillations that would be simple in a sharply layered planet appear split into several closely spaced signals. The splitting implies that the modes are interacting with a region where composition changes gradually, and stable layering can support additional motion. In plain language, the interior seems to have more structure than a compact core beneath a uniform envelope. Inversions of the ring waves favor a diffuse central region, extending to roughly 60% of Saturn's radius. Within this broad region, heavier elements appear mixed with hydrogen and helium rather than confined to a small, sharply bounded object. One influential analysis found a total heavy element content on the order of 17 Earth masses within the diffuse region. Neither number is a direct picture. The rings measure wave patterns. Researchers infer which internal oscillations can generate them, then solve for distributions of density and composition that reproduce those frequencies, while also respecting gravity measurements. The result depends on the physics used for hot compressed materials, the assumed rotation, and the permitted ways that composition changes with depth. Gravity and seismology constrain different aspects of the same hidden planet. Spacecraft tracking reveals how Saturn's total mass departs from a simple sphere. Several distributions of material can produce very similar external gravity. Oscillation frequencies respond to how density and composition change within the planet, adding information that the broad gravity field alone cannot provide. Even together, the data do not select every ingredient uniquely. Their value is that they eliminate families of interiors that once seemed equally plausible. The strongest conclusion is therefore not that Saturn contains a core with a photographed edge at exactly one depth. It is that a compact rock and ice ball beneath a fully mixed hydrogen envelope does not explain the combined evidence as well as a broad transition enriched in heavy elements. The word core survives, but its meaning changes. It names a deep region where composition becomes progressively heavier, not necessarily a separate solid sphere. This reframes the descent. At the cloud tops, you lost the idea of a surface. In the metallic region, you lost the idea of ordinary gas. In the central region, you lose the tidy boundary that many cutaway diagrams promise. Saturn becomes denser and richer in heavy material with depth, but nature is not required to place a line where a textbook would find one convenient. There is another consequence. If part of the diffuse region is stably layered, material there resists simple overturning. Heat and composition can then move differently from the way they would in a fully convective interior. That affects the planet's oscillations and long-term cooling. Ring waves are valuable because they can distinguish some of these possibilities, even though the central material itself remains inaccessible. The reasoning has now traveled in both directions. Atmospheric motion led downward to the interior. Interior motion traveled outward through gravity and wrote a pattern into the rings. To read that pattern, however, you must stop treating a ring as a smooth band. The recorder works only because it is made from separate orbiting particles. That fact took centuries to establish. When Galileo turned a telescope toward Saturn in the early 17th century, the small and imperfect view did not reveal a ring. He described a central body accompanied by structures on either side, and later saw their appearance change as Earth crossed the ring plane. The geometry was beyond the resolving power of his instrument. Christian Huygens, using a better telescope, proposed in the middle of that century that Saturn was surrounded by a thin, flat ring that did not touch the planet. This explained why the appendages changed as the viewing angle changed. At some seasons, the ring opened toward Earth. Near a ring plane crossing, its narrow edge nearly disappeared. The ring still seemed capable of being one solid structure. James Clerk Maxwell tested that possibility mathematically in the 19th century. He showed that a uniform solid ring could not remain stably centered around Saturn. A continuous fluid ring also faced instability. A system made from many independent pieces could preserve the observed form, because each piece could orbit according to its distance from the planet. Theory predicted separate motion before telescopes could resolve individual pieces. Near the end of the 19th century, James Keeler used spectroscopy to test it. Light from one side of the ring was shifted differently from light on the other because the material moved toward or away from the observer. More importantly, the inner portion moved faster than the outer portion, just as orbital motion requires. A rigid ring would have shown the opposite relation because points farther from the axis travel faster when a solid object turns as one. Modern observations confirm the particulate ring directly and add composition. The bright main rings are dominated by water ice, which reflects sunlight efficiently. Particle sizes range from fine grains through pieces comparable to familiar objects, with larger bodies embedded in parts of the system. Dust and darker contaminants are present as well. There is no one representative ring particle that tells the whole story. The icy composition is measured through the way reflected sunlight changes with wavelength. Water ice absorbs particular bands of light, leaving a spectral pattern that instruments can recognize. Brightness at different viewing angles and radio signals passing through the disk add constraints on particle sizes and packing. These methods sample collective behavior, so the answer is usually a distribution rather than an inventory. An opaque patch can contain more material, larger particles, tighter packing, or some combination that must be separated with additional observations. Even the word particle spans an awkward range. A dust grain and a block broad enough to damage a spacecraft are both particles in orbital dynamics because each follows its own path. The term does not mean that every piece is microscopic, nor does the smooth appearance imply that spaces vanish between bodies. Sunlight reflected from an unresolved population fills those spaces in the distant view. From a distance, those separate bodies merge into bands. Across the ring plane, the bright system spans hundreds of thousands of kilometers. Through much of the main rings, the vertical thickness is on the order of only 10 meters. Local structures can rise much higher, especially where a moon or a strong wave disturbs the plane. So 10 meters is not a universal ceiling. It is a useful statement about how extremely flat the main disk usually is. That proportion is difficult to preserve in a mental picture. A diagram thick enough to see almost always exaggerates the vertical dimension. If the broad disk were reduced to the width of a large city, its ordinary thickness would be closer to that of a building than a towering wall, while rare disturbed regions could rise above the surrounding plane. The comparison is only for geometry. The real disk is not a continuous plate, and its thickness varies with location. Why does such a broad disk become so thin? Particles begin with small motions above and below the average plane. They collide. A collision does not remove orbital motion, but it can convert some relative motion into heat, deformation, rotation, or fragmentation. Repeated collisions damp the random vertical component. Gravity and conservation of angular momentum keep the material orbiting, while collisions guide most paths toward a shared plane. This also answers why the particles do not simply fall into Saturn. Gravity is pulling them inward at every moment. Their sideways speed carries them forward fast enough that they continually miss the planet. That is an orbit. To spiral inward, a particle must lose orbital energy and angular momentum through collisions, drag, electromagnetic forces, or some other interaction. Gravity alone does not command an immediate drop. It provides the inward acceleration that bends the path. Inner particles complete an orbit more quickly than outer particles. That difference is called shear. Imagine two neighboring lanes of material at slightly different distances from Saturn. The inner lane gradually moves ahead. Any temporary clump is pulled lengthwise by the differing orbital speeds. This shear prevents much of the ring from behaving as a permanent frozen mosaic. Yet the particles do not ignore one another. In dense parts of the rings, their mutual gravity gathers material into temporary elongated concentrations. Collisions and Saturn's tidal pull keep disrupting and rebuilding them. These self-gravity wakes can change how much light passes through the rings depending on viewing direction. They are measured through brightness and occultation patterns, then interpreted with dynamical simulations. They are not solid ridges fixed in place. The same competition creates a ring that can transmit organized disturbances. Suppose a moon gives ring particles a small repeated pull whenever their orbital rhythms line up in a particular ratio. One tug is weak. Repetition adds coherently, producing crowded and sparse regions that wind into a spiral density wave. The visible stripe is a pattern passing through particles. Individual pieces enter and leave the compressed region, while the wave carries information and redistributes momentum. Density waves reveal properties of the disk. Their wavelength changes with distance from the resonance. That change depends on the amount of ring material and on the balance among gravity, collisions, and orbital shear. By measuring the wave, scientists can estimate local surface density. This is one reason the rings can serve as a scientific instrument. Their response turns a small periodic force into a structure large enough to measure. Resonance does not make gravity mysteriously stronger. It makes timing important. A gentle push delivered at random can cancel an earlier push. A gentle pull repeated at the right phase can accumulate. The moon and the affected ring region then exchange angular momentum. Depending on the geometry, ring particles can be urged inward or outward, while the moon experiences an opposite reaction. The change in any one orbit is small, but a coherent pattern acting across countless particles can maintain a visible boundary or wave. The wave does not carry its form without cost. Collisions among particles and the disk's collective gravity alter the disturbance as it travels away from its resonance. The pattern can spread and weaken while transferring energy and angular momentum through the ring. Measuring that evolution helps distinguish a dense region from a sparse one. It also prevents a common misunderstanding. The stripe seen in an image is not one permanent row of ice being dragged around Saturn. It is a moving organization of many orbits. What happens when a body is too small to clear a complete gap? Some embedded objects still have enough gravity to deflect nearby particles. The result can appear as two offset, wing-shaped interruptions around the unseen or barely resolved body. These features are called propellers because of their outline, not because blades are turning or pushing material. Cassini followed some propellers over years. Their changing positions showed that embedded moonlets interact with the surrounding disk and do not always follow perfectly unchanging paths. The observation is the pattern moving through the rings. The moonlet's size and mass are inferred from the scale of the disturbance and from models of how particles respond. A propeller is therefore both an object trace and a reminder that even modest bodies can exchange momentum with a vast disk. The Roche limit provides a wider boundary for this discussion. Close to a planet, tidal gravity pulls more strongly on the near side of an object than on the far side. If an object is held together mainly by its own gravity, a sufficiently large difference can prevent loose material from assembling or can disrupt a vulnerable body. Saturn's main rings lie in a region where these tides make the growth of a large gravitationally bound moon difficult. The Roche limit has no universal wall at one radius. Its location depends on the densities of planet and orbiting material, the body's structure and spin, and the strength holding it together. A small, strong fragment can survive where a loose aggregate separates. Collisions can weaken or compact a body, while Saturn's tides and orbital shear keep disrupting larger assemblies. The ring becomes a granular disk, negotiating between gathering and disruption. By now, the smooth oval seen from Earth has become a hierarchy of motion. Each particle follows an orbit. Neighboring orbits shear past one another. Collisions flatten the disk. Mutual gravity builds transient wakes. Moons drive waves and shape boundaries. Embedded moonlets write propellers. The ring never turns as one object. The next question is where its material and momentum go. The answer reaches into Saturn through what is often compressed into two words: ring rain. Those words hide several different measurements, and keeping them separate is the only way to understand what Cassini actually found. The first channel was recognized from Saturn's ionosphere. From Earth, astronomers mapped infrared light, produced by a charged form of hydrogen high above the planet. The brightness did not vary randomly. Bands of altered emission at low latitudes lined up through models of Saturn's magnetic field with particular regions of the rings. The best explanation is that charged water products leave the rings, follow magnetic field lines, and enter the ionosphere. There they change the abundance of free electrons, and therefore change the infrared signal. This is rain only by analogy. It is not liquid water falling through a blue sky, and the telescope did not watch individual drops. It is a chemical and electrical fingerprint, interpreted with a model of the field that guides the material. Cassini later encountered a second channel directly. During its final orbits, a dust detector collected grains only nanometers across in the space inside the D-ring. Their composition and motion pointed back toward the main rings, especially the B and C rings. Impacts can eject tiny fragments, and once a fragment is small enough to carry an important electric charge, compared with its mass, magnetism can redirect a path that gravity alone would have set. Yet these nanograins represented less than 1/10 of the relevant impact ejecta in the estimate. They were a real sampled population, not a census of everything leaving the rings. Then came a third channel. Flying through the narrow region between the planet and the innermost rings, Cassini's mass spectrometer sampled a chemically rich equatorial influx. It detected water, methane, ammonia, carbon monoxide, molecular nitrogen, carbon dioxide, and more complex organic material. For the band, time, and trajectory that the spacecraft sampled, researchers inferred a flow of roughly 4,800 to 45,000 kilograms each second. That is a striking range. It is also one of the easiest Saturn numbers to misuse. The spacecraft did not wrap an invisible measuring cup around the entire planet. It crossed a special place during a special phase of the mission. Converting local densities into a flow requires assumptions about speed, latitude, ionization, geometry, and how the stream changes with time. The upper end of the range is not a permanent global drain valve. It cannot be multiplied by the ring mass to produce a trustworthy date for the last ring particle. The measurement tells us that substantial material was moving inward through the sampled region then. It does not tell us that the same amount leaves every latitude in every season for millions of years. These three channels can interact, but they are not interchangeable. One is an ionospheric pattern, consistent with charged water products traveling along field lines. One is a directly collected population of electrically transported nanograins. One is a composition-rich influx sampled by a mass spectrometer near the equator. Put them together, and the old picture of an isolated planet under a separate ring disk disappears. Material and charge cross the apparent boundary. Keep them separate, and the evidence remains stronger, because each claim can be tied to the instrument that earned it. Cassini could make those measurements, because its last path was deliberately unusual. After years of observing from safer orbits, the spacecraft repeatedly passed through the gap between Saturn and the inner rings. Radio tracking responded to tiny changes in its motion, helping researchers separate the pull of the rings from the gravity of the planet. Dust and gas instruments met material that earlier trajectories could not sample. A magnetometer carried the field measurement closer to its source. The region that looked empty from far away became a laboratory full of particles, fields, and flowing chemistry. The route could not continue forever. Cassini had no way to remain a controlled, sterile visitor after its fuel for precise navigation ran out. An uncontrolled future collision with Enceladus or Titan would have carried a small but avoidable risk of terrestrial contamination. So the mission ended with a commanded plunge into Saturn's atmosphere. Planetary protection was not an ornamental explanation added afterward. It was part of the logic of the final experiment. The same path that protected the moons also turned the spacecraft into a probe of the space between ring and planet, until the atmosphere ended the signal. Before that final descent, the same grand finale orbits turned Cassini into a falling test mass. During selected passages between Saturn and the rings, Earth stations sent a stable radio signal to the spacecraft and received a coherent signal back. If Cassini moved toward or away from Earth a little faster than expected, the received frequency shifted through the Doppler effect. The change was tiny, but repeated tracking turned it into a precise record of the spacecraft's motion. How can that motion weigh rings the spacecraft never touched? Gravity changes an orbit. Saturn pulled Cassini strongly toward the planet, while the rings added a much smaller pull in a different direction. Flying through the gap placed the spacecraft where those contributions had a geometry that earlier orbits could not provide. The ring signal could finally be separated from much of the signal caused by Saturn's flattened shape. Separated does not mean read from one number. Researchers reconstructed Cassini's path with a dynamical model. It had to include Saturn's total gravity, the uneven gravity associated with its shape, the influence of deep winds, the gravity of the rings, the spacecraft's starting position and velocity, and smaller forces and tracking effects. The calculation then worked backward from the measured Doppler record to the combination of hidden quantities that best reproduced it. That backward problem is an inversion. Inversions require care because different causes can imitate part of one another's signal. A change assigned to ring mass might otherwise be absorbed into a slightly different description of Saturn's gravity or the spacecraft's acceleration. The grand finale geometry helped break that overlap because the planet and rings tugged Cassini from different sides. The investigators also tested alternative dynamical treatments. Some small accelerations remained incompletely explained, yet the estimated total ring mass stayed comparatively stable across those tests. The result for the main rings was roughly 2/5 of the mass of Mimas, with an uncertainty of roughly 1/8 of a Mimas mass in either direction. This was a gravitational estimate of the combined mass of the principal rings. It did not locate every particle, and the masses of individual rings were much more difficult to separate. The uncertainty is part of the measurement, not an optional footnote. Most important, mass is not an age display. A lighter ring can become polluted or spread differently from a heavier one, so mass changes the rate predicted by an evolution model. But turning that input into a date requires assumptions about the ring's starting mass, the arrival and retention of dark material, collisions, spreading, and loss into Saturn. Cassini weighed the present rings. It did not watch their birth. To ask when they formed, we now need several clocks, and we need to know what each clock actually measures. Those measurements invite a tempting calculation. If material is falling in now, how long until the rings are gone? The honest answer is that no single observation starts such a countdown. To see why, you have to separate 4 different kinds of time that are often blended into one dramatic claim. Formation age asks when the present ring material, or the present ring architecture, first assembled. Exposure age asks how long the visible ice has collected dark material from incoming dust under a chosen set of assumptions. Structural age asks how long processes such as collisions, viscosity, resonances, mass loading, and ballistic transport would need to shape the profiles seen today. Erosion or lifetime asks how the rings may change in the future if particular loss and transport rates persist. Those clocks can influence one another, but they do not have to show the same time. Imagine finding a clean stone beside a road. Its clean surface might mean the stone arrived recently. It might instead mean that impacts knock dirt away, that rain washes the surface, or that an older stone was broken to reveal fresh material. The age of the exposed face is not automatically the age of the stone. Saturn's rings demand the same discipline, with far more complicated cleaning, mixing, and recycling. Cassini's dust detector measured the flux of tiny incoming particles near the rings. The rings are overwhelmingly bright water ice, with only a small fraction of darker non-icy material. In 2023, researchers combined the measured dust flux with assumptions about how Saturn's gravity focuses incoming particles, how efficiently impactor material sticks, how pure the rings began, and whether the flux was roughly steady. Under those assumptions, the low pollution level corresponded to an exposure time of no more than roughly 100 to 400 million years. The calculation dated exposure under its chosen assumptions, not formation, change, focusing, or retention, and the clock changes, even though Cassini's detector counts remain the same. What if an impact leaves far less contamination than expected? Simulations published online in late 2024 in the 2025 journal volume produced that possibility. A fast micrometeoroid can vaporize material, and some charged products can escape instead of remaining as contamination. In those simulations, the effective fraction of pollutant retained by the ring could fall below about 1%. A numerical ring particle remains simpler than a real one. Porosity, granular texture, material strength, electrical charging, chemistry, and the surrounding plasma are difficult to represent completely. The result allows a clean surface to survive longer than a full retention model predicts. It weakens one root, from brightness to youth, without proving great age. How does the ring's nearly flat geometry change what arrives? A 2026 recalculation found an effective focusing factor about 5 times lower than in the earlier treatment. In its baseline case, a nominal exposure time moved from about 500 million years to about 2 billion years. When possible cleaning and low retention were included, still longer exposure histories became possible. The revised geometry opens older exposure histories without revealing a birthday. Cleaning, retention, incoming particles, ring mass, and ring arrangement can all change. Several combinations of starting condition and later evolution can produce similarly clean ice now. Composition alone, therefore, cannot securely determine when the rings formed. Structural age adds another layer. Ring particles exchange momentum through collisions. Impacts can launch ejecta that land somewhere else, transporting mass and angular momentum. Resonances keep forcing particular places. Viscosity spreads some structures, while self-gravity gathers temporary ones. A model may ask how long a proposed starting disk needs to become the profiles that Cassini measured. That time describes the evolution of architecture under the model. Older material could be recycled into a younger-looking structure. A young disruption could also inherit material that existed long before the disruption. The arrangement and the ingredients need not share a birth certificate. Future lifetime is different again. Ballistic transport and mass loading models can reproduce inward flows of thousands to tens of thousands of kilograms each second for chosen conditions, and some yield evolutionary times from roughly 15 to 400 million years. Those times depend on impact flux, focusing, impact yield, viscosity, mass history, and recycling. Parts of the rings may thin, spread, fall inward, collect onto moons, or be redistributed at different rates. Even disappearance needs a definition. No instrument has measured one fixed expiration date. Brightness samples particular surfaces, particle sizes, and illuminated depths, while collisions and ejecta can turn, bury, dilute, or remove contaminants. Every step between a bright surface and a formation event must therefore be tested. The most useful next measurements would attack those steps directly. Researchers want better constraints on how much impactor material is retained, how charge separates vapor from solid debris, how quickly contaminants are redistributed, and how ring mass and viscosity changed in the past. Origin models must also make predictions that can be checked against the inner moons and Saturn's tilt, not merely reproduce a pale ring in isolation. A date will become persuasive only when several independent clocks agree for the same physical reasons. The formation question remains open for the same reason. A clock built from pollution or loss cannot reconstruct a starting event by itself. Every proposed history owes the same evidence a reckoning: ring mass, ice purity, moon architecture, Saturn's tilt, and the 4 disputed clocks. One broad possibility is that some ring material has survived since early in the Saturn system. In that case, recycling, impact vaporization, loss of pollutants, and changes in ring mass would have to help preserve the unusually ice-rich appearance. This is not the old idea of an untouched primordial disk sitting unchanged for billions of years. Survival would mean continuing evolution, with the material repeatedly rearranged and perhaps cleaned. Another class of models begins with a large differentiated satellite. Such a body could carry a rocky interior under an icy outer layer. If it passed close enough to Saturn under suitable conditions, tides could strip much of the ice while the denser interior was lost to a different fate. That offers a possible route to an ice-rich ring, but it requires a particular satellite, orbit, and sequence of interactions. No remnant has been identified as a label proving that history. A different lost satellite model gives the hypothetical moon a name: Chrysalis. In that calculation, the moon's orbital evolution helped connect Saturn's present tilt with interactions among Titan, Saturn, and other bodies. A later instability sent Chrysalis close to Saturn, where disruption could provide material for relatively recent rings. The model is valuable because it tries to explain the planet's tilt and the rings within one dynamical history. Chrysalis remains a proposed body inside a model. Cassini did not discover its wreckage or record its destruction. Other simulations begin with a collision between middle-sized icy moons. Debris from the impact can be sent inward, disrupted by tides, and redistributed into rings and a new inner moon system. These calculations test whether impact speeds, debris composition, and later dynamics can resemble what exists now. They do not establish that a particular collision occurred. A successful simulation shows that a route is physically possible under its assumptions. It is not a recovered recording of the past. Primordial survival, tidal stripping, a lost moon such as Chrysalis, and collisions among icy moons are therefore competing histories, not chapters of one settled biography. Each must face the measured ring mass, the high ice fraction, the orbital arrangement of the moons, Saturn's tides, and the disputed clocks. A future solution may combine processes rather than choose a single clean event. The rings could preserve old material in a structure assembled later, or young material could have evolved faster than a simple clock suggests. The present evidence does not force one answer. Enceladus supplies matter. Cassini measured a strong concentration of dust around its orbit and imaged jets emerging from the Moon's south polar terrain. Those jets feed particles into the broad, faint E-ring. At least one part of Saturn's ring system is being replenished now by a moon. That fact matters here because it closes a circuit of material. A moon supplies dust. The particles respond to gravity, radiation, and electromagnetic forces. Some remain in the diffuse ring, some strike other bodies, and some eventually leave the system or move inward. The detailed questions about what lies beneath Enceladus belong to a different story. In this one, the moon is a working source inside a larger machine. How can a moon reshape a ring it never touches? Mimas transfers momentum through repeated gravity. At the 2-to-1 inner Lindblad resonance, a B-ring particle completes roughly 2 orbits for each orbit of Mimas. Hundreds of Cassini occultations showed that the outer B-ring edge carries the forced pattern alongside free modes and time variation. This is the same timed exchange seen in density waves, now measured at a named edge. Titan carries that exchange outward into orbital migration. Cassini images and radio tracking allowed researchers to follow its orbit with extraordinary care. 2 independent analyses found that Titan was moving outward by about 11 centimeters each year over the measured era. That is much faster than older models with a simple, constant tidal response had expected. Titan's measured outward migration is consistent with tidal transfer of angular momentum from Saturn's rotation into Titan's orbit. One leading explanation is resonance locking. As Saturn's interior evolves, the frequencies of internal oscillations can change. A moon can remain near a moving tidal resonance, allowing the transfer to stay efficient as the resonance itself shifts. This is a model for the mechanism, not a direct view inside the planet. The outward motion was not guessed from a single photograph. Researchers compared positions across years and modeled the forces affecting the orbit. Astrometric images supplied one route. Radio tracking of Cassini during encounters supplied another. Their agreement made the migration difficult to dismiss as a quirk of one technique, while the explanation for the unexpectedly rapid rate still required a model of Saturn's changing interior. The present rate must not be projected backward as a ruler with the same spacing for billions of years. Saturn's interior changes. Its oscillation frequencies change. The moon's distance changes. Other moons interact. The significance of Titan's measured migration is not that it supplies an easy age. It shows that the planet's interior, its rotation, and the orbits around it are dynamically connected now. Magnetism crosses the diagram too. Deep inside Saturn, motion in conducting hydrogen-rich fluid is inferred to sustain an internal dynamo. Far outside, the resulting field organizes charged particles and helps couple the planet to its rings, moons, and the solar wind. Cassini's final close passes made the internal field easier to separate from currents flowing through the surrounding magnetosphere. The result was one of Saturn's sharpest puzzles. The large-scale internal magnetic field is extraordinarily close to symmetric around the rotation axis. Some grand finale measurements constrained the tilt of the dipole to less than about 7/1000ths of 1 degree. That does not mean perfect alignment. Higher order structure is present, and scientists have to subtract the influence of external currents to infer what comes from within. But among planetary magnetic fields that have been measured, Saturn's is unusually axisymmetric. That near alignment explains the unreliable radio clock encountered earlier. The deeper question is how Saturn's dynamo produces such extreme symmetry. One family of models places the dynamo below a stable, electrically conducting layer. Such a layer could act as a filter, weakening rapidly varying or non-axisymmetric components before the field reaches the observable exterior. Some magnetic inversions allow that filtering region to be more than roughly 2,500 kilometers thick. Cassini did not see a layer at that depth. The number belongs to models that can reproduce aspects of the field. Other interior arrangements may also contribute, and the dynamo itself remains an active problem. Outside the planet, the field does not create one simple magnetic bubble. Cassini detected energetic protons in the narrow region between Saturn's atmosphere and the D-ring. The particles are consistent with processes that begin when cosmic rays produce neutrons, followed by decay and interactions that leave charged particles trapped by the field. Rings and moons absorb particles, dividing the wider radiation environment into zones. This is a structured radiation belt, not evidence that Saturn itself is radioactive. At the poles, auroral light shows another part of the circuit. Changes in the solar wind can compress the magnetosphere and reorganize the main auroral oval. Rotation and internal plasma matter too. Material supplied by moons joins the environment. Currents flow along magnetic field lines, and atmospheric gases emit light after energetic encounters. No single sentence saying the sun causes the aurora or the moons cause it captures the coupled system. Auroral light is therefore the visible end of a much larger electrical route. Hubble and Cassini could record changes in the glowing polar pattern, but that light did not reveal every charged particle responsible for currents elsewhere. It showed where energy reached the atmosphere strongly enough to make gases emit photons. To follow the route away from that bright endpoint, scientists needed instruments that responded to different physical carriers. If Saturn's rings and moons absorb energetic particles, why did Cassini still find a belt of energetic protons between the atmosphere and the D-ring? Absorption does not erase every particle everywhere. A ring or moon removes particles whose paths intersect it. That selective removal helps separate the wider particle environment into zones. The proton belt and the absorbing bodies are not contradictory findings. The bodies help shape the boundaries and populations that the detector measures. The distinction becomes clearer when you ask what each instrument actually receives. A camera receives photons. Hubble and Cassini could map auroral light because atmospheric gases emitted enough photons toward them. The same camera could look into a region filled with sparse charged particles and record darkness. Darkness sets a limit on visible brightness. It does not prove that the volume contains no particles. A particle detector answers another question. It counts particles that enter the instrument and measures properties such as their energy and direction. That is how Cassini could identify an energetic proton population along its own path, even where no luminous cloud marked the belt. The detector did not photograph a global shell, It sampled the local population, and repeated measurements constrained how that population was arranged. A magnetometer receives neither a picture nor a particle count. It measures the local magnetic field as the spacecraft travels. Changes in the field help researchers reconstruct the environment through which charged particles move and the currents that modify it. Camera, particle detector, and magnetometer are not three names for the same observation. Each makes a different link in the causal chain available to measurement. A polar glow, a proton count, and a field change can therefore belong to one explanation without becoming interchangeable. The camera locates emitted light. The particle detector samples a population directly along Cassini's path. The magnetometer measures the field that guides charged motion. Together, they turn apparently empty space into a structured environment and make the next inward path of ring material physically traceable. Different impact products follow different pathways. Charged water products can alter the ionosphere. A small population of charged nanograins can be transported inward. Neutral or ionized gases and organics can join the equatorial influx. Cassini measured evidence for all three channels without establishing one universal path, followed by every grain. Ring dynamics require more than gravity, and magnetospheric physics requires the rings. That interdependence is what Cassini's final plunge made tangible. The spacecraft passed through a boundary that photographs had taught us to imagine as clean. On one side was a bright ring, on the other was a pale atmosphere. In between, the instruments found matter, current, radiation, and gravity carrying information in both directions. The planet and rings were not separate exhibits. They were exchanging pieces of the same evolving system. The rings' birthday remains open, but their motion does not. Cassini measured incoming dust and sampled particles and gases in the ring-planet gap. Their origins and flow rates were inferred from those measurements, while impact simulations indicate that some pollutants may escape. Each instrument and model has narrowed one part of a system that no single clock or diagram can freeze. That is not a weakness in the portrait. It is what a close portrait looks like. From far away, uncertainty can be hidden along with motion. A bright line seems like a single object. A pale band seems quiet. A moon seems parked in place. A magnetic field seems like an invisible outline. Close measurement separates each of those impressions into processes with rates, directions, and limits. Return now to the telescope. The ring plane still looks clean enough to draw with one stroke. Saturn's globe still carries those soft bands, and the whole arrangement may still feel composed. Nothing in the evidence requires you to trade that beauty for a darker story. The beauty was never the error. The error was mistaking unresolved motion for absence of motion. The rings are orbiting particles colliding, gathering, spreading, and responding to moons. Material is crossing from ring to atmosphere through more than one channel. The moons are migrating, supplying dust, and returning gravitational rhythms to the disk. Conducting fluid deep inside the planet is inferred to maintain a magnetic field that carries consequences far above the clouds. Even the clean ice is an argument still changing, as better models test what the measurements can mean. Distance made all of that look quiet. It compressed millions of separate orbits into a line and buried chemistry inside a patch of black space. It turned a changing system into an icon without making the icon false. Saturn remains beautiful when the still image opens into motion. Perhaps it becomes more beautiful because the order is not painted on. The order is being made continuously by rotation, gravity, collisions, waves, tides, fields, and time. Nothing here is still. The universe still holds more questions than answers. If exploring them feels like home, subscribe, and I'll meet you on the next journey.